Good day and welcome to the second part of our discussion, the types of discontinuity. The targets for this lesson are to illustrate the different types of discontinuity of functions at a number, to classify the discontinuity either removable or essential, either by graphing or by solving. And number three, to redefine functions with removable discontinuities. As illustrated in the graph, if f is continuous, then the points on the graph of f approach the point A, f of A, on the graph. And as you can see, there will be no gap in the curve. But now let us consider this graph. At which numbers is f of x discontinuous? Why? By looking closely, we can begin at x equals 1. At x equals 1, it looks as if there is a discontinuity when x equals 1, because the graph has a break there. The official reason why the function is discontinuous at x equals 1 is that f of 1 is not defined. If we look at x equals 3, we see that the graph also has a breakpoint, but the reason for this discontinuity is different. Here, f of 3 is defined, but the limit of f of x as x approaches 3 does not exist, because the left side and the right side limits are different. So f is discontinuous at x equals 3. What about at x equals 5? Here, f of 5 is defined, and the limit of f of x as x approaches 5 exists, because the left side and the right side limits are the same. But the limit value and the functional value are not the same. So, the function is discontinuous at x equals 5. Looking at the last point, at x equals 7, we see that the function has a vertical asymptote at x equals 7. Clearly, the graph has a break at this point. And by definition, the limit of the function does not exist. Thus, it is discontinuous at x equals 7. These examples of discontinuity can be classified into two major categories. The first one is the removable discontinuity. Suppose the limit of the function exists at that point, but either the functional value is undefined or the functional value is not equal to the limit value. Then we say f of x has a removable discontinuity at x equals a. Again, it is important to note that the limit of the function exists in this removable discontinuity. The second type of discontinuity is essential discontinuity. Suppose the limit of the function as x approaches the point A does not exist. Then we say that the function has an essential discontinuity at x equals a. Moreover, we can classify two types of essential discontinuity, and they are, first, jump essential discontinuity. If the limit of the function from the left and the limit of the function from the right both exist but are not equal, then the function is said to have a jump essential discontinuity at x equals a. And the second one is the infinite essential discontinuity. If the limit of the function from the left or from the right approaches positive or negative infinity, then the function is said to have an infinite essential discontinuity at x equals a. Let's go back at the examples and classify these types of discontinuity. At x equals 1, we see that the limit at x equals 1 exists, but the functional value is undefined. Therefore, the function has a removable discontinuity at x equals 1. Meanwhile, for x equals 3, though the left side and right side limit exist, they are unequal. Therefore, the function has a jump essential discontinuity at x equals 3. Graphically, we could easily see that it is indeed a jump essential discontinuity, because the values of the function jumps from one point to the other. For x equals 5, we see that the limit exists. However, the functional value is not equal to the limit value. Therefore, the function has a removable discontinuity at x equals 5. And clearly for x equals 7, we see that the limit does not exist. In this case, in particular, we see that it is positive infinity. Therefore, the function has an infinite essential discontinuity at x equals 7. And now let's try to look at example of functions where the graph is not given. Let us discuss the continuity of h of x at x equals 1 if h of x is defined as follows. First, let us look at the functional value at x equals 1. H of 1 is equal to 2, based on the definition of the function. Now let's proceed on investigating the limit value. The limit of h of x as x approaches 1 is 1 minus 1, which is basically 0. We see that the functional value is not equal to the limit value. Moreover, the limit value exists. Therefore, we say that the h of x has a removable discontinuity at x equals 1. As you can see, the graph of h of x is a line with a hole at x equals 1 and a solid dot at point 1, 2. In this case, we could actually remove the discontinuity of the function. The removable discontinuity of a function can be removed by defining the value of f of a so that the functional value would be equal to the limit value at x equals a. So, how do we do that? We redefine the function h of x as follows. To remove the discontinuity at x equals 1, since the limit of h of x equals 0 as x approaches 1, then we redefine h of x as follows. We say the capital H of x would be h of x when x is not equal to 1 and 0 when x equals 1. Now, looking into the graph of small h of x, after redefining it becomes this kind of graph. We see now that the function becomes continuous. So in general, if x equals a is a point of removable discontinuity, then we can redefine the function f of x as follows. To be capital F of x, defined as a piecewise function, where it would still be f of x for those values where x is not equal to a, and to be the limit of f of x as x approaches a, where x is a point where the function experiences a removable discontinuity. So to wrap it up, number 1, there are two types of discontinuity: removable discontinuity and essential discontinuity. Essential discontinuity can be classified into two further categories. First is the jump essential discontinuity. Second is the infinite essential discontinuity. And last one, we can always redefine the function to remove its removable discontinuity. That's it. I hope you have learned so much regarding the topic of types of discontinuity.